Hi, I'm Stacey and welcome to my YouTube channel. In this video, I am going to be starting from the always block. I'm going to be explaining what an always block is, how you use it, why you need it, and we're going to be working from there through to why we need a clock in the FPGA and what an inferred latch is. So we're going to take a bit of a journey today from always blocks to synchronous logic to inferred latches. And these are very critical topics for someone to learn about if they are learning how to program an FPGA. And so I hope that you will enjoy. I'm going to be starting this from a software point of view because I find that a lot of people coming into FPGA design do it from a software background. And one of the biggest mistakes that people will make is they will try and treat this like conventional programming. And it is not conventional programming. We are not programming a CPU. We are describing a circuit. And I'm going to start with the always block because I find that the always block doesn't really have a software analog. It's a bit of its own thing. It can be a bit difficult to understand how it's going to behave. And there isn't really a software equivalent. So I am going to start by focusing on this always block. We don't really need to worry about this other code. I think actually what I'm going to do is just kind of move this down like this so that we don't really have this other code in the screen. We just have this code, which is what we want to focus on. And what is this code? So I have a state counter. This is a logic signal. This is system Verilog. So if you were doing this in VHDL, everything would be different, but this is system Verilog. The principles behind the design are still going to be the same whether you're coding in system Verilog or VHDL. The logic is just saying that this is going to be 32 wires, and the 32 wires are going to be indexed. 31 is the MSB, all the way down to 0 is the LSB. So it's 31 down to 0, and that's going to be my 32 wires. And this way I am specifying the indexing of the wires. And my counter is going to behave in the way described by the always block. So this part of the always block is called the sensitivity list. And my sensitivity list in this always block contains a clock. If there's a clock, you can't have anything else but a reset. You can have clock and reset and nothing else. There are other always blocks that have other things, but in this case, for a synchronous always block, which is the kind of always block we're looking at today, it is a clock and a reset maybe, and then nothing else. So in order to explain how this always block is behaving, I am going to write it in another way that will be more familiar to someone who's got a software background. So instead of doing always here, I am going to create an inline assign statement. An assign statement just connects my wires to something. And so you can have assign state counter. So for example, if I set assign state counter equal to 0 or driven by 0, that would mean those wires are connected to ground. But we don't want that, we want this. So I'm going to write my assign statement in the same way logically as this. So this always block has multiple functions. One of the functions of it is just the logic, right? It's the behavior of the signal. And I'm going to describe that here. The other function of this always block is to register the signal. And that I'm going to explain in a moment. So let's first focus on the functional, and then we will focus on the register. So we are going to start, this is an inline assign statement, just like your other programming languages like Python or JavaScript. We have an inline if statement here. So I'm going to do, my first condition is if I'm in reset, then I'm going to drive state counter with 0. We don't need all that. We just need this. This apostrophe is used to indicate that all of the bits must be 0. So this duplicates this 0 for all bits. Otherwise, if state counter is not equal to next state, then also 0. Otherwise, state counter is driven by state counter plus 1. Okay. So we're just going to make it look a bit nicer. So this is the format for an inline assign statement in System Verilog. It is basically a mux. For this condition, it has this value. For this condition, it is this value. For this condition, it is this value. And so this functionally and logically is behaving the same way as this. So I've taken the if statements that are in these nested if statements, and I've condensed them into one line. So there is one very important thing that is included here, and that is that state counter is driving itself. State counter is on the left and the right hand side of this assign statement. And in a conventional programming language, that would be okay. But when you're designing for FPGAs, you can't do this. This will infer a latch. So when we get a little bit later on in the video, I'm going to be explaining what an inferred latch is and why you can't do this. And my goal is really to explain why, for you to understand the underlying principles behind what's going on here and really understand why we're inferring a latch, what a latch is, and why it's bad, and what this clock is doing. I want you to really understand what's going on inside the FPGA, because we can learn things by rote. We can learn to put a clock here, and that's a good thing to do. But what's actually going on? That is what we're going to discuss now. So, as you can tell, this always block, as I mentioned, has got two functions. It's got the logic behavioral function, which is this guy that we've just reproduced, but it also has a clocking function, which is that it registers the signal. And in order to reproduce that in this format, I am going to do this. I'm going to take this bit of code here, like that. I'm going to take out the reset. There we go. And now I'm going to create a state counter new, because we can't drive a signal by itself. This is not allowed. And so instead of doing that, I'm going to make this state counter new. And then I'm going to use this always block to register state counter new into state counter. And now this is now a complete reproduction of this code. These are equivalent, which means that they will be converted into the same circuit inside the FPGA, and that conversion process is called synthesis. So these pieces of code will be synthesized into the same circuit inside the FPGA. Okay, so let's talk about why I need this here and why I can't drive the signal by itself. So if we take a look at this block diagram, this is the block diagram of the circuit inside the FPGA that gets synthesized. And I've highlighted two signals here. I've highlighted a blue thicker signal that's long, and I've highlighted a red shorter signal. And there is a problem that we have inside the FPGA. We have the problem that the signals do not travel through the FPGA instantaneously. There is a propagation time, and this propagation time is through the physical wires, like this blue one and this red one, but also through the blocks inside the FPGA. If you have an adder or a multiplier or some kind of logic block, we have to take into account the propagation time through those blocks in the FPGA. And the problem comes when we have signals that are different lengths. So for example, if I have a short signal that this is a short propagation time, and I have this long one that's got a long propagation time, and I want to process them together here, then what will happen is this signal will arrive relatively quickly at its destination, and this one will take longer. Now these are both really small times as far as FPGAs are concerned, but the relative times between each other, that's the issue. So if we see here, if we have the starting point where both signals go high, or both signals are valid, and then the red reaches its destination and also is valid at this time point, because this is the time axis, and then the blue signal takes much longer to get to its endpoint and is valid only at this time. And so if I want to combine my signals together, I can't do it during this transition time, because it will be an indeterminate value. I don't know how long it's going to take for blue to propagate, and so I can't reliably combine my signals together. But beyond this here, we know, okay, both red and blue have arrived at this time, and so I can use those signals. So what we need is a way of saying, this is when the signals can change, and this is when they stay the same. And so we create ourselves the safe zone. And the safe zone is the time where the signals will have guaranteed arrived. So they will have a time that they are changing and the time that they are stable. And we use the clock edge for this. The rising clock edge is the delimiter of our safe zone. And we have a setup time, which is the time before the clock edge that the signal must have arrived. And the hold time is the time after the clock edge that the signal must have be stable. And so using the clock edge, we are able to create a safe zone around my signal to say, okay, this is when I want to use my signal. The process of calculating these timing values, the propagation of the signal through the device, through the wires and the blocks in the device, this is called static timing analysis. And static timing analysis is extremely important inside the FPGA to ensure that the signals are stable when they need to be stable and that they're changing when they're supposed to be changing. So you might say to me, so Stacey, hold on. What if I don't want blue to have to travel this far? I don't like this. This is too far. I want to have my blue signal right here so that I can use it immediately. I don't want to have to sit and wait for it to travel all the way through there to use it. It uses up half my clock cycle. I want to be able to use it right here. So what we can do is inside the FPGA, there are memory elements called registers. And the registers inside the FPGA will store a local copy of the signal here, right? So if you want to create a local copy, it will make a local copy there. So that if you want to store the signal because you want to use it and it takes too long to propagate, you want to give yourself a bit more time because it's closer. And how do we do this? We do this. So this is called a register. It is a memory element inside of the FPGA, and that is important. It remembers. So this is memory. So this is a 1-bit physical memory. You can make your bus longer, but the smallest size of this is one bit. And what will happen is we have our clock. I've moved my clock to the top, and over the time the blue signal is changing. Sometimes it's yellow, sometimes it's orange, sometimes it's green, but when the rising edge of the clock happens during the safe zone, it is blue. And so here the blue signal gets driven into the data input, and the register takes a snapshot at this point in time, and it remembers the value of the blue signal at the rising edge of the clock, and then it outputs that value for the rest of the clock cycle. So for the next clock cycle, it will maintain that value, and that is my local copy. So if I want to make a local copy of a signal, I can type this. And what this will do is this tool will take a look at the code I wrote. It will recognize this format. FF is flip-flop, which is another name for register. This will turn it into this. And so this is a basic building block inside the FPGA. The FPGA is made up of fundamental electrical logic units like registers, but it also has LUTs, which are lookup tables, which aren't clocked memory. They don't have a clock input. They just decide between signals, just like the code I wrote earlier. That was a mux, and that mux will be synthesized into a LUT, and it doesn't have a clock. And so this fundamental building block of the FPGA, it's like a little Lego block. Like the FPGA is a bunch of little Lego blocks that you build together, connect together. This one will make a local copy of my blue signal and call it blue registered. And blue registered will live here, closer to where it needs to be used. So the FPGA synthesis tool will put the registers closer to in strategic places so that they are closer to where they are used. So now you can see I am registering state counter into state counter new. And that is remembering this value and storing it into state counter. There are a couple of other critical things about this. I alluded to the fact that you can't have state counter driven by itself. You can't do that. Let me show you why. So here we have my logic. This is my non-clock logic. There are other logic inside the FPGA that's asynchronous, that doesn't create a clock, like a mux. For example, this code will be synthesized. It doesn't have a clock. See, there's no clock here. So this means that this is going to be synthesized into a memory element, a clocked memory element, and this is going to be synthesized into non-clock logic, so asynchronous logic. So if there is a clock, then it's synchronous, and if there is no clock, then it's asynchronous. So this is what synchronous logic looks like, and this is what asynchronous logic looks like. There are other ways to write asynchronous logic, but for now, this is good. And this is going to be turned into a LUT, and this is going to be turned into a register or FDRE. These are my registered clocked logic, and you can tell it's got a clock because there's literally a physical clock input, and this is synchronous, and this is synchronous, and this is my asynchronous lookup table logic, so it doesn't have a clock. And so you can see that we can delimitate our logic, and there is this mental delimitation that FPGA designers have, especially if they are experienced, is to differentiate between what is synchronous and what is asynchronous. So synchronous logic looks like this. It has a clock input. Asynchronous logic doesn't have any clock inputs. What happens if we do this? So now I am feeding a signal back inside my asynchronous logic. And so what the static timing analysis tool that I mentioned that measures the signals of the path. If we go back here, it's easy, you start there, you end there, you've got this length of the path, and the static timing analysis is going to take the lengths of the paths from one memory element to another. And the clock needs to be the same clock to go from one memory element to another. If it's not the same clock, it's a clock domain crossing. And again, you have timing issues. You have issues with your static timing analysis. This is why it's extremely important that you use the same clock for signals for their source and their destination. Very important. So we have one clock that's driving both of these, and the static timing analysis tool is going to measure the signal distance from there to there, and also the clock propagation time, because that's also not instant. And how is it going to do that? Here. Because this path is now an unknown length. Because if the signal is feeding back on itself, it has an unknown behavior. It might oscillate. It might stabilize. We don't know. And the tool can't guarantee how long it's going to take to arrive at its destination. And that is the critical part, is that this delay time is now unknown. And so as a result of that, this tool is not able to properly perform static timing analysis on this path. And so because it's not able to, in order to make an effort to stabilize the path, what the tool will do is it will put in its own fake memory element that's like a register. So this is a hacky memory element, and all its job is to stabilize the signal in the return path. but it can't do its job properly because it doesn't have a clock. And it can't give it a clock. The tool can't put a clocked element here because I have to tell it what clock to use. As the designer, I have to say you must use this clock. And so the tool doesn't have enough information to be able to put a proper register here. And if it did, it would also change the behavior of the signal, because then this would be delayed, because remember, the register, the output of a register is for the following clock cycle. And so that will also change the behavior of the signal. This is called an inferred latch. And so when we are inferring a latch, we are putting a hacky memory element. The tool is automatically putting a hacky memory element inside of a loopback path inside the FPGA. That is what's happening. So anytime you have a loopback in asynchronous logic, the tool is going to need to infer a latch. And that is why we say that you mustn't do that. We don't highly not recommended to put loopbacks in asynchronous logic. So for example, if I go back to my code here, if I have this is a loopback in my asynchronous logic. Sorry, this is asynchronous because there's no clock in this code, and I am driving a signal by itself. So I am looping it back. And the tool is going to be forced to infer a latch in this case. I can get around that by going state counter new, where now I am not driving the signal by itself, but I am putting the signal through a register in order to put a clock in the return path. So if we go back here, this is what I'm doing. So I am saying, okay, I don't want you to put a hacky memory element there. I am going to choose the clock because I know what I'm doing. I'm the designer. And I am going to put in a memory element in this return path. And this gives the tool what it needs to be able to perform the static timing analysis. And so that is what I'm doing when I write this code. I am telling the tool to put a register in the return path of this loop. And that is what this code is doing as well. This code and this code are exactly the same. All that I'm doing is I'm combining this logic inside here, where I'm putting if statements inside my always block, but functionally it's identical to this. I'm just combining them all into one. And this is why these things can be quite weird, because it's like, why is there a clock there? What is the clock even doing? So when we break up this into the synchronous and asynchronous parts, it becomes a lot more clear what's going on. I do want to mention a couple of more practical things about this code and about inferred latches. We can make an always block that doesn't have a clock. If I were to take this clock out, that would remove the register behavior, the register functionality from this block. And then this and this are identical. So this is another way of writing this. And by removing the clock, I also remove this clock functionality. So I am no longer registering the signal. I just have it in as asynchronous. The one other thing I will mention is that I can leave out else statements here. If I just do this, then there is no other case included in this. I literally just have if reset, and now what must it do? What must it do? What's here? What is it going to do in the else case? Because I'm not defining it. I'm not defining the behavior of the signal for all cases. Now, what the synthesis tool is going to do is literally the only thing it can do. It's going to have the signal maintain its value. Because what else can it do? It must just stay the same. That's the implied behavior. If you don't define the behavior, it stays the same. The signal is going to stay the same value, right? The problem with that is that that requires a memory element. In order to stay the same value, I need to remember what the value was. That's what the tool's going to do. The tool is going to imply the maintenance of the value. And that implied maintenance of the value requires memory. This is going to infer a latch. I am looping the signal back on itself in asynchronous logic. And so this is going to infer a latch. So if we leave out this else statement, it is going to infer a latch because the tool is going to try and maintain the signal's value, which means it's going to loop back in itself on asynchronous logic. How do we fix it? Pausage clock. Just that simple change. I also have to make these into arrows, which is an annoying quirk of system Verilog. That simple change will tell the tool, you need memory because you need to remember the signal value from as it was to maintain it. Use this clock to create that memory. And by specifying the clock, I am telling it to create a register that is memory that's clocked in order to maintain this value. So this means that whenever you have an asynchronous always block that doesn't have a clock in it, you need to ensure that you are covering all your cases, like making this a value of 1 in your off state. And you need to make sure that you are not looping the signal back on itself inadvertently, because that is what is going to infer a latch. This also comes up in in default cases in case statements. So for example, in this case, I have an always block with no clock in it and I miss a case. The tool is going to attempt to maintain the value of that signal because it has nothing else to do with it. And when it does that, it is going to loop it back on itself inside the lookup table. This lat is the building block, the fundamental building block inside the FPGA that is going to synthesize this code. And it will behave as if the output is looped back on itself. That is a loopback in asynchronous logic. And that means that we are going to get a latch. And that's what an inferred latch is. An inferred latch is a loopback in asynchronous logic. So if we are to summarize what we learned, an always block has two functions. A behavioral function, which is how the signal is going to behave, aka this bit. And it also has a registered clocking function, which is to register the signals, which means that it creates a local copy of the signal so that you can use it. And it can also create a register in a loopback path so that it doesn't infer a latch. These are the functions of the always block. If we drive a signal by itself, then we will infer a latch in asynchronous logic. Synchronous logic is logic that contains a clock, like this always block. Asynchronous logic is logic that doesn't contain a clock, like this mux. Synchronous logic can loop back on itself because the register will be inside the loopback path. Asynchronous logic shouldn't be looped back on itself because then the static timing analysis tool is not going to be able to know how long the signals are. The tool is going to put a hacky memory element inside the loopback path, and that hacky memory element is called an inferred latch, which means that all of your default cases and all of your cases for the behavior of a signal need to be covered in asynchronous logic in order to avoid looping a signal back on itself. Now, so hopefully now you'll have a better understanding of how to avoid an inferred latch by understanding exactly what an inferred latch is, and that you can use always blocks to store local copies of signals so that you can have more time to do stuff with them. Thanks so much for watching my video. I have not been around for a while. It's mostly just because of family stuff going on behind the scenes and a couple of other projects that are taking some time. I am still around. I am still doing things. I have upgraded my setup a little bit. So hopefully that is going to help the quality of my videos moving forward. And yeah, it's nice to be back. I'll see you around.